Hello everyone, welcome to another video of my channel. In the previous video, we used a version of Common Filter to do a 7 to 14 days rollout of our supply chain to assess and see which action to take to minimize both of the expected costs and tail costs. Now, that rollout depends on the fact that we have chosen a good set of parameters for our model. So, for example, let's say we try to model our lead times. So our lead time could be a mixture of two log normal distribution. How do we know that we have chosen a good set of average and variance for our model? So here we use a version of Monte Carlo, specifically the Hamiltonian Monte Carlo, to sample the parameter space. So here is the overall picture of what we are trying to do. We are trying to choose a good set of parameters that would best describe our supply chain manifold. So for example, one set of parameters could tell us that the supply chain is currently stable. Another set of parameters could tell us that the supply chain is currently unstable due to some change in policy. So we have a bunch of scenario, right? A bunch of world for the supply chain, the state that it could be in. Once we have chosen a set of supply chain manifold, then per manifold, we do a 7 to 14 days rollout. In the last video, right, from the rollout, we calculate various metrics like expected cost and tail cost. But another cool thing you could calculate is, see how the path interact with the risky region. We want to know, okay, how long does the path stay in the risky region, right? And we want to know, okay, how many of those points go inside the risky region. So basically, we try to see how turbulent the path are in the rollout. Now, so how do we find these parameters? There are various methods, but all the method pretty much in the realm of the Monte Carlo. You could try to randomly walk and create a proposal to whether accept or reject, but the acceptance rates would be very low. You could use the Langevin motion, but that is pretty decent. But in general would head toward the mode, right? We want to have a good set of distribution. So um, instead of viewing these as distribution, what we do is that we turn that upside down so that it becomes a physical landscape. Once it becomes the physical landscape, we can augment that with momentum so that we could talk about the kinetic and potential energy. Imagine a ball rolling on that physical landscape. It has kinetic energy and physical energy. So here is a closer look at what we were referring about in the previous slide, right? So we have our parameters manifold, right? So these, parameter, we stack up all the parameter from the various thing that we're trying to model, the lead time, the yield rate, demand, the pressure and capacity and so on. So for each set of parameters, right, it would tell us a slightly different story of how our supply chain is currently, right? So, and then once we have chosen a supply chain manifold, then we use the common filter to do, a 7 to 14 days rollout, right? So basically, the parameters tell, okay, which supply chain were we in? And then per world, okay, maybe we roll out to 7 to 14 days. Now, for those of you that have seen, Adventures Infinity Wars, remember there was a scene where Doctor Strange tried to go through 14 millions and something were, right? And then per were, he would roll out to, he would forward in time to see when they would be successful in defeating Thanos. And there was exactly one uh, case where they would defeat him, but it was at the sacrifice of Iron Man. So here in this, supply chain algorithm, we hope that we don't sacrifice something as large as losing Iron Man. So here we take a closer look at the common filter that we went through in a previous video, right? Once we have chosen our parameters, right, then we have our model. Once we have our model, then we would do, rollout. And then from the rollout, right, then we would choose the best action that would minimize all the costs and all the risks. So, let's say you have two action. In action one, the overall cost is small, but could be very risky. Um, and then action two, right? The cost could be slightly more, but is a lot safer. So, in choosing an action for our supply chain, there are many things that we have to consider. We, of course, right, consider cost, and of course, then we also consider the risk in choosing that particular action. So, for us to use various methods from Monte Carlo, what we do is that we would take the density function and turn it upside down. The reason we do that, right, so that we turn that into something physical. And in the physical realm, we can talk about potential energy and kinetic energy. So this here, right, would provide us the kinetic energy. And then once we augmented the momentum, we would see that the motion of a random particle would be much more efficient. So here we take a closer look at the Hamiltonian dynamics. Recall earlier that we turn our density function upside down so that it would become a physical landscape. Imagine a ball rolling from the top of the mountain down to the valley. At the top of the mountain, the potential energy is high, while the kinetic energy is low. But at the valley, is reversed. Potential energy is almost zero, while the kinetic energy is very high. But the total energy is always conserved. Now, this is our potential energy, and this is our kinetic energy. And we can prove that the total energy is always constant. So here, why do we say that it is approximately constant when it is constant? Well, later, we will see, to get this path, we have to use something called the leapfrog integrator. And leapfrog integrator produce a point where the energy changed slightly. It's very, very minimal. So because the energy changed slightly, we have to use something called the metropolis hasting to decide whether we accept or reject that new proposal. So here is our truth. This is the part that keep us in motion. Once it's in motion, it would be in motion unless the curvature prevent it from going further, right? Or the curvature itself could make it go faster. Now here, this is we call this the mass matrix. Ideally, we would want this to be dynamic, but that would be pretty much intractable in, say, supply chain where the dimension is too high and the manifold is just too darn complicated. Using a global mass matrix is enough, and this is calculated from by calculating you have a set of burn-in parameters from the running the Monte Carlo, and then you calculate the covariance from that. Um, So this, would keep you in motion, and this would bend your direction of travel. Um, so there's a good video on Hamiltonian Monte Carlo from Dr. Drew Holbrook from UCLA. It's pretty darn good. In general, a lot of these videos on YouTube, they explain it in a very analytical way. I'm a more visual person. I like to do things in terms of geometry. But that video has many good practical advice for us to run the Monte Carlo. So here we take a closer look at the various way to sample our parameters. So actually, we're not really working in the parameter manifold. We are working in the energy surface given by the Hamiltonian equation, because the Hamiltonian is constant, and that energy surface lives inside the cotangent bundle of the parameter manifold. Um, we have the random walk method, but the random walk just randomly walking, right? You would produce a lot of points where the acceptance rate is extremely low, so you are very inefficient. Or you could use the length-driven motion, where you pretty much try to minimize the KL divergence using the gradient. It's slightly inefficient because you still have that jitter from the Brownian motion. Furthermore, because it is a gradient ascent, you head toward the mole, right? Remember, the mole is the peak when you view it as density, but when you turn it upside down, become your valley. So it would head toward the valley. But what we want is we want to explore the distribution, not just give us the one that is most plausible, but actually give us a distribution of parameters. And combining with leapfrog, it provides us an algorithm that's actually very, very efficient, where the acceptance rate is extremely high. So here we take a closer look at some of the comments we said earlier about the cotangent bundle. So down below, we have our parameter manifold. And lines above all of that is the cotangent bundle. And inside that cotangent bundle is the energy surface given by the Hamiltonian equation, because the Hamiltonian equation is constant. Let's say we have always start with some theta 1, right? And then we go inside the cotangent bundle, we have our fiber. So our fiber is pretty much just our momentum manifold. Okay, so you would choose a random momentum, and then you would start exploring. But each exploration point is jumping to different fibers. So basically, your movements is inside the energy surface given by the Hamiltonian energy equation. And then, right, you would finally, after some iteration, depend on your choice. You could do 100 iteration or 15 iteration, and also, depends on what is your step size. So you reach your second point, and then you can decide, whether to accept it or not. So here we take a closer look at the leapfrog integration. Um, I remember the first time I see this method, I just thought to myself, how in the world do people come up with so many things like leapfrog or like Monte Carlo? It's just so so darn brilliant. Someone like me would never be able to um, come up with these things. I mean, I even I have a hard time understanding it, but I can't imagine what it would take to come up with a lot of these things in mathematics. Um, all right, so how does it work, right? You just do half step in momentum, full step in position, and half step in momentum. Um, the and then you would compose these over and over, right? And then you would stop after say 30 steps or 50 step, depend on how many you want to do, and then the epsilon is your step size. The thing about this is that all the steps are reversible. The reason we want it to be reversible so that the detail equation is balance is conserved, right? Remember, we want that because um, we want our target distribution to be the stationary distribution. In other words, if we keep running this thing, then eventually our sample um, would be on that distribution. And of course, in the beginning, we would throw away some of the sample, and those are called burn-in. So overall, this integration method is so darn clever. It utilizes the geometry of the space at every single step. It's extremely, extremely clever and extremely efficient. So here we see how we go from one proposal to the next. Right here we have L steps with step size. So we would use the leapfrog method to get a bunch of points, and we would stop when we reach the proposal L. One thing to remember is that these points lies or approximately lies on the Hamiltonian energy surface. And I say it's approximately, right, because the leapfrog method in at the end of the day is just an approximation method. So it would, because of that error, we would utilize metropolis correction, where this is your alpha, the minimum between one and this ratio, and then we would draw u uniformly from between 0 and 1, right? So this help us. This provides the action to whether accept or not, right? If u is less than, it could be less than equal to, right? If it's less than alpha, then we accept. But u is greater than or equal to alpha, then we would reject, right? This is very standard in Monte Carlo. So when we finish running our Hamiltonian Monte Carlo, not only should we save the sample, but we should also save the potential energy score, because the potential energy score tells us the density. So what we would do is, we would choose, let's say, top 60% of the sample based on the potential energy. And then we're going to cluster them using a certain distance function that still respect the geometry. And we're going to cluster them, and we're going to look for something called the medoe within each cluster. Now, I have a big issue calling it a medoe. Why don't they call it a medoe, right? Because it's like median. The fact that it's medoe is bothering me. I don't know why. So each medoe would be representative of the current state of the supply chain, right? Instead of using all the sample, that would be too much. We would choose a representative from each medoe, right? And then from each representative, we would do a 7 to 14 days rollout. So here we take a closer look at the clustering of the sample of the parameters. For us to do, clustering, of course, we have to have some kind of distance function. So here, distance function, use the Mann-Halobis distance, and this is the matrix that we used earlier for the Hamiltonian Monte Carlo, so that at least we still, respect the geometry somehow. Or maybe you could calculate this from computing covariance of all the samples that you have chosen. Maybe it could be pretty much very similar. And then if you whiten the sample using this matrix, right, you would get the same thing here. And then you would choose the points in the middle of your cluster, right? This is different from the centroid, because the centroid takes the average. In general, when it comes to high dimensional data and probability, you never ever want to take the average, because the average would destroy your geometry. And sometimes you would land at a point that not even in your space anymore. Here in this case, it wouldn't even be in your cluster anymore. Um, like in this case, right? Then here's the mean, which is not very useful, but this is the middle way, right? Um, which is more representative of our cluster. Once we have cluster of our samples of parameters, we have our representative from each cluster, and from each representative, right, we would get a supply chain manifold, and from each supply chain manifold, you would do a 7 to 14 days or 30 days rollout, and from each rollout, right, from each set of rollout, you would calculate various metrics like costs and risks and so on, and from these metric, right, you would create a final cost or risk, right, by doing a weighted metric where the weight it just pretty much depend on the cluster size. And there's many ways to do weight, but I feel this is probably easiest to do. Now, we would also need a representative um, for online forecasting, right? So I would choose, say, the biggest cluster and choose a representative from that, and that would be something that's always running daily. That would tell us how the world is on a daily basis. When something change, we have something that can be run very quickly. While the Monte Carlo, something that we run weekly because that takes a lot of resources. So here we are doing a quick review of the Kalman filter, specifically a local ensemble transform Kalman filter. Right, we have an ensemble of points. Each point is a different, scenario for our supply chain. So we would, in the forecast, we would push forward the point, right? Push forward that in time, and whenever we have a new observation or new data come in, then we use that new data to push our um, ensemble to a more appropriate location. And we, in general, we would like to approximate that using the tangent manifold, right? But in high dimensional data, and with functions that are not nice, we can't work with tangent manifold. What we do is we approximate with the with something called the anomalies, right? Basically, just imagine in calculus you use secant line to approximate tangent line. Same thing here. You would approximate using something called anomalies. All right, so this guy would be here, would be an approximation to our tangent manifold. Now, from all that, you calculate, the something called the Kalman gain, right? In this high dimension would be a giant matrix where it would pull back your observation error, right? This is called the innovation. It would pull back this innovation back into your state manifold, and it will tell you, whether to accept more of the current forecast or more of the observation. And then, so basically, in the analysis, the final point that you pull to is just a weighted combination of these 2 points, right? So basically, you're trying to balance between observation and forecast. That's all. So here, finally, we have what we want. So remember, we choose representative from the parameters manifold, and for each representative, we do 7 to 14 days rollout. Remember, each representative is different supply chain work or different supply chain manifold, and per manifold, right, you would do a rollout. And every time you do rollout, you do all kind of metric. You could do cost metric, or you can see how often you land in a risky region. And because you have a number of supply chain manifold, right, you would do appropriate weighted metric from that. So here, right, you would do weighted metric from the cost, or you would do weighted metric from the how often you enter the risky region. So overall, right, I understand this whole thing is very hand waving, and to be honest, I'm not sure how effective this would be. So I am intending to go further into this and try to implement some kind of algorithm on perhaps Databricks.